Welcome back. In this video, we're going to look at the Brandt Hall outbreak simulation. Now, this simulation can be used to model various kinds of outbreaks, but the most common would be a cold or something happening about partway through a semester that people on the floor start to get sick and it just spreads all the way through. So what we want to see is how we can simulate something like that physical spread of a cold on a floor plan of a hall. This one is for Brandt Hall. So what we have is the floor plan that's been folded in a way to create a little channel, and then I have a number of beams equal to the number of rooms that I'm considering inhabitable, excluding the bathrooms, the laundry, the stairs, that kind of thing, study. And I'm going to start out with a certain number infected and then count how many are infected, are total infected each turn, and how many new infections or change in the number infected I get. And I'm tracking those two numbers because the first number, the number infected, is a population count, whereas the change in the infected is the rate of change in that population count. It's a discrete or an approximation of a derivative. And so what we're going to do is develop data for both population and derivative change in that population, and then develop a differential equation model to relate to this data. So, start out, I'm going to choose a certain number. Let's start with 1. One of these floors is going to be infected, so I choose 1. I'm going to start somewhere in the middle. And for the sake of simplicity, I'm going to assume that any beans that fall in the middle area are safe in a sense. If they don't land in a room that has an X, they're safe. If they do land outside of the floor, like they fall off the edge of the floor or they go into the wrong second floor instead of the third floor that I'm counting, I'm going to re-roll them on top. So I've removed 1 bean. This is the infected pile over here. And I'm going to scatter the other beans, starting somewhere around the middle. Not too high up, but a little bit to give us a little change. Notice a couple of them fell off there. 1 dropped off the edge over here. If I had a partner and I have them holding their hands on the edges to block the beans from falling off the edges. Oh, looks like 1 fell off the edge of that floor. So I'm going to re-roll these. Whoop. Okay. So I look through and I want to identify any beans that are touching rooms with X's. Now there's only 1 room with X. So I look through and I see there's 2. And so I'm going to move the other ones away from it. There are 2 that I'm going to add to my infected pile. So I started out with 1 infected population, and then I'm going to go to 3. So I write my derivative or my change in the infected as 2. And to identify 3 rooms that are infected, you can mark X's on 2 other rooms. Now, for simplicity, I'm just going to assume that they're nearby and mark X's on rooms next to or nearest to this room. Now, you could take a more random approach and just choose spots at random, but what we really wouldn't want to see, I want to see, is how something spreads outward from an epicenter. So that's interesting to see. If you wanted to just see how it filled the whole space, then you could just choose rooms randomly. But I want to kind of see how it spreads. So I will then add, I have 1, my starting, and then I add 2, so my next change. And I'm going to re-roll the others, just slide those off, and I will continue this process until all the rooms are infected. Now, why is that? Well, let's think about it. Right now, my simulation is based upon things getting infected. There's really no way in my simulation for the beans to get better or the infection to go away. Now, of course, when people catch the cold, they get better. So it's not realistic in that end. But we could think of this as a short time frame where if they get the cold, they're going to have the cold for a little while. So like say a week or so. And so we're doing these simulations in matters of hours or days. Okay. So I look down, I see being on 1x there. And just want to see which ones are actually touching rooms. Okay, I got one there. Okay, so I end up having 4 beans that got infected this time. Again, these are human beans, right? Representing. So my derivative has now gone from 2 to 4. So I'm increasing my derivative as I go up. And I'm going to mark 4 more x's on rooms. So I'm not going to count the bathroom, the stairwell. Jump across over here, the nearest room. 1, 2, 3, 4. Let me just pause for a second here. As you can see, the x's will kind of spread outward. You'll have this diffusive property where the concentration of the infection kind of just spreads outward and outward and outward until the entire floor is covered. Now, it may take a while. It's entirely possible that my beans will land in the safe zones and will delay that growth, that spread of the infection. And really, if we think about it, there are physical parameters that are controlling the rate of growth. For example, how high up I drop the beans determines the amount of energy in the beans as they fall and bounce. That'll determine how far outward they can spread. Also, I'm dropping them in near the center, which is near where the infection starts. So that will encourage the growth. Also, the size of the beans relative to the room is a factor. The number of beans that can fit in the room determines what's the maximum number of beans that could get infected at any point in time. But if we think about kind of the bigger picture, we see that not only is the number of rooms that are getting infected growing, but at the beginning, the rate of change, the derivative, is also growing. And the question is, will it stop? Well, if we think about the cold spread in general, you know that there's a certain finite amount of beams, certain finite number of rooms in this floor. At some point, they will all get infected, or all that can be will be infected. And at that point, the infection will stop, at least in this area. So we know that the rate of change, even though it seems like it's growing at the beginning, will come to a point where it's 0. It'll stop at some point. And we want to do as the differential equation is think about the shape of that derivative. It starts out near 0, increases upward, and somehow comes back to 0. What's it look like? How does it look like going from the beginning to the end? Well, you have data collected for yourself. In graphing that data, you'll see certain patterns in the shapes. And then when you look at your differential equation options in D field, you'll see similar shapes. And that's how we start with a comparison. Is there a qualitative similarity between the model and the data itself? Or at least the model and how we understand the data. And then once we have that qualitative match between them, then we can dig into the numbers and we can try to fit the parameters of our model to get as close to the data as possible to see if there's a quantitative fit. And that in the spreadsheet is outlined by two values really. One is the trend line that you're comparing the slope, the derivative slope information, which is based upon the data, rounded a little bit from the change in infected to the derivative averaging nearby changes. The trend in that slope comes from a linear regression model that Excel or online spreadsheet has built into it. And that will give us an R-squared value, which is sometimes called the coefficient of determination. The other value is called the sum of square errors. And this is just based upon the difference between the modeled value and the actual values of the population as they go. And looking at the differences, if you square those differences and add them all up, you can quantify and compare one model's approximation to another based upon the different parameter values. So that's how the simulation is set up, whether you did it yourself or you're working with someone else's data. You can see examples of the data collected. The number infected, of course, is what we were tracking, the number of beans that we're removing from the sample. The number susceptible is the leftover beans that we're shaking on there. And we can relate those two directly because we know that the total stays the same. The susceptible plus infected always equals the total. In this case, it was 26. The change infected was our approximation of the derivative, and that's based upon how many newly infected beans we pulled out each turn. And then to make that approximation a little better, we take the average of it. This is one of the main methods of smoothing out a discrete derivative to get a more continuous version. There are other ways to make it more accurate, but this is a very simple, straightforward approach just by averaging across. Then we have the model component, and that relates to the models you're given or deriving. I gave you several examples to look at for models, and then computing the value of the slope functions here, you can compare the derivative to those values and see if there is a nice consistent slope. And that's graphed over here. Is there a linear relationship between the model component and the data? And this one looks pretty good. Has an R-squared value of 0.972. So that's a very good fit. Now once you have the model established, a qualitative form, then you work on the parameter values and then enter in the value of the model with those parameter values fixed and compare to the actual data right up here. And the difference squared is added up down below. That's the square errors, and the sum of the square errors is shown below. Now the sum of square errors is going to be a fairly large number. But what you can tell is as you change the parameter values, you want to look to see if the sum of the square errors is getting smaller and smaller and smaller. And so you can tweak the parameter values a little bit to get that sum of square errors as low as possible. And usually we want to get it down to about 2 digits So like maybe close to like 20. All right, now it's at 4,000. So if we can reduce it down to 3 digits, or on 100 down to 2 digits, that is a significant improvement. And then you'll graph the model against your data. So I have the data here, this little S-shaped curve, and I want to, once I have the model figured out, graph that model against the S-shaped curve, and then compare the derivative of, oh, and this is already set up to compare the derivative of the data. So that's your change in the data um, averaged out, so the derivative information versus the actual data infected. I want to see if is there a relationship between the rate of change and the population itself. So the first model that we looked at earlier is the exponential model. And you can see that this is also not a very good model because the population would just keep growing, growing, and growing. Okay? Or shrinking, shrinking, shrinking to zero. Well, we don't have either of those. Well, this is different though. How about a b minus ax? That gives us a population that comes up and converges towards a certain value. Now, if we look back at our data, we had something very similar to that. See how it converged up and over? So we have that kind of asymptotic shape to it. But then it also has another asymptote at the beginning. It seems like it's coming up from 0 and then meeting this term. So when you compare the other, the other equations, differential equations, you're looking for some of that pattern, some of that shape and relationship and the overall curve, and also looking at this shape relating the derivative itself to the population. Now this, of course, is not the graph that we're looking at in the D field. This is what's called a phase plane. And we'll phase diagram. We'll look at those a little bit later in the class. But right now, it's a way of relating a change in a variable to the variable itself instead of the variable to time. So that's kind of a peek ahead. The D field itself will graph the variable related to time.